Hey everyone. We've been studying exponential functions and log functions, and today we're going to change gears a little bit and study limits, certain types of limits. So the topic, indeterminate forms. So we want to study what are called indeterminate forms. There's various things called indeterminate forms, and so let's see what those are. So if limit as x approaches a of f of x equals 0, which equals limit as x approaches a of g of x. So we have a couple of functions, we take their limits, and we get 0 for each of them. Then when we look at the limit as x approaches a of the fraction f of x over g of x, we don't say that this limit is equal to 0 over 0, although if you computed each of the limits individually, right, to compute the limit at the top and the bottom individually, what you'd get is 0 over 0. We don't say it's equal to 0 over 0. What we say is that this is indeterminate of type 0 over 0. So when we say that it's indeterminate, we are not saying that it's equal to 0 over 0. What we're saying is that it requires further analysis. We don't know what the limit is at this point. It's indeterminate. So that's the indeterminate form of type 0 over 0. And then in the same vein, if limit as x approaches a of f of x equals plus or minus infinity, which equals limit as x approaches a of g of x. So now we have a couple of functions. When we take the limit of the first function, we either get plus or minus infinity, and for the second one, we also get plus or minus infinity. And by the way, they don't have to match. One of them could be positive infinity, and the other could be negative infinity. That's fine. Then, when we look at the fraction, limit as x approaches a of f of x divided by g of x, we say that this is indeterminate of type infinity over infinity. And we don't worry about whether it's plus or minus infinity and plus or minus infinity. We just say it's infinity over infinity. And what this means is we don't know the answer. We don't know what the limit is at this point. We need to analyze it further. And one thing to point out here, I'm writing a as if it's a number, but in this setting, we allow a to either be positive infinity or minus infinity. So just say here, we allow a to equal plus or minus infinity. So in the limits that we're computing here, a could be a number, a could be positive infinity, a could be negative infinity. In any of those cases, when we get a situation where we get 0 over 0 or infinity over infinity, we say that they're indeterminate forms of the given type. So for example, let's look at the limit as x goes to infinity of let's do 3x squared plus 2x plus 1 divided by 4x squared minus x minus 2. You probably encountered this limit in Calc 1. And hopefully you learned this. I mean, there's a trick for computing this, but in the end, when you compute the limit of a polynomial over a polynomial and you're going to infinity, if the degrees match, then this becomes an easy limit to compute. This turns out to be 3/4. When the degrees match, we've got degree 2 polynomials in each case. All we do is take the ratio of the leading coefficients. But notice, right, so we get 3/4. But notice, this limit right here is indeterminate of type infinity over infinity, right? If you take the limit individually of the top, you'll get positive infinity. Take the limit as x goes to infinity of the bottom, you also get infinity. So this is indeterminate of infinity over infinity, but we know from previous Calc 1 rules how to compute this, right? You get 3/4. Now, what we need, so in Calc 1, you learned a way to deal with taking limits as x goes to infinity over polynomial or polynomial. But in many cases, we don't know how to deal with this, so what we're about to learn is what's called L'Hopital's rule. And L'Hopital's rule gives us a way to deal with indeterminate forms if we have 0 over 0 or infinity over infinity. So it goes like this. If limit as x approaches a of f of x divided by g of x is indeterminate of type 0 over 0 or infinity over infinity, then the limit as x approaches a of f of x over g of x is equal to the limit as x approaches a of f prime of x over g prime of x. So this gives us a way to handle indeterminate forms of type 0 over 0 or infinity over infinity. We compute, instead of computing the limit of f of x over g of x, what we do is we take the derivatives of each of the functions individually, so compute f prime, compute g prime. When you compute this limit, if you get some number, that number will be equal to the original limit that you're looking at. So let's see how this goes in action. Oh, and before I move on though, L'Hopital's rule applies for left and right hand limits also. So let's say note L'Hopital's rule, which I usually just abbreviate with an L apostrophe H, applies to left hand. That's kind of weird. You want to say left hand limits. Left hand, right hand limits as well. So remember, a left hand or right hand limits, those are the ones where you put a little plus or a minus right there. And so for left hand limits, what it would say is that, or sorry, I guess that's a right hand limit. So putting little pluses here, still true. And if you put little minuses here, also true. We get equality. Okay, so let's look at some examples. First one. So let's look at limit as x approaches infinity of natural log of x over x. Now, if you compute the limits individually, we learned about the graph of the log function as x goes to infinity, natural log approaches infinity. So this is indeterminate of type infinity over infinity. Never write that this is equal to infinity over infinity, but off to the side, just to sort of keep track of what's going, I put an infinity over infinity. That means then that we can apply L'Hopital's rule. Whenever I apply L'Hopital's rule, I'll put a little LH right there to indicate I'm about to use L'Hopital's rule. And so according to L'Hopital's rule, this is equal to the limit as x goes to infinity of, let's see, the derivative of the numerator is a 1 over x. The derivative of the denominator is a 1. And so now this is equal to the limit as x goes to infinity of 1 over x, which we know is equal to 0. So by one application of L'Hopital's rule, we were able to show that this limit right here, right, just follow the equal signs, is equal to 0. Okay, next example. Limit as x goes to infinity of e to the x divided by x. If you compute the limit of the numerator individually, right? Think about the graph of the exponential function as x goes to infinity, e to the x goes to infinity, same with the denominator. So this is indeterminate of type infinity over infinity, which means that I can then apply L'Hopital's rule. This gives me limit as x goes to infinity, take the derivative of the numerator, you get e to the x, take the derivative of the denominator, you get a 1. And now we can say that this limit is equal to infinity. Oh, and I forgot to put my little LH there. Yeah, on a test or a quiz, you're not required to put an LH there, but it's always in your best interest to indicate, to show me that you know what you're doing, so that if you make some sort of arithmetic mistake, I can see you know what you're doing, you just made a simple mistake. So it's nice to show, okay, I know that I can use L'Hopital's rule right now, and here I go, I'm applying it. So I'll always try to remember to put an LH there as I go. Before I move on to the next example, I'm going to just ask the question, how do you interpret these two limits that we computed? The first one, we showed that as x goes to infinity, natural log of x over x approaches 0. Now what does that tell us about this fraction right here? Well, as x gets very, very large, if this fraction is approaching 0, what it tells us is that the denominator is growing much, much faster than the numerator. And so a way to remember this, polynomial always beats log. The polynomial function grows much, much faster, right? In the second example, and you probably heard the term exponential growth, this is what it means. What we have is the exponential function over a polynomial function, and we get infinity. That tells us that the numerator is growing much, much faster than the denominator. Exponential functions always beat polynomial functions. Okay, next example. Let's do limit as x approaches 0 from the positive side, sine x over x. So compute individually as x approaches 0, the numerator and the denominator are both approaching 0, so this is indeterminate of type 0 over 0, which means we can apply L'Hopital's rule. That's equal to the limit as x approaches 0 of, now I take the derivative of the top and I take the derivative of the bottom, and so we have cosine x over 1. As x approaches 0, cosine is approaching 1. And so we get 1. So what does that tell us then? As x gets close to 0, sine x and x are almost exactly the same, right? Because we get a fraction equal to 1. Okay, another example. Let's do limit as x approaches pi over 2, 1 minus sine x divided by cosecant x. So, oh, I was looking for my drink. So, as x approaches pi over 2, what do we have here? As x approaches pi over 2, sine x approaches 1. And so that means that we get a 0 in the numerator, but cosecant of x is equal to 1 over sine. The denominator is approaching 1. So this, I guess I should say, is this is a warning. Not always when you're handed a limit of some fraction are you going to get an indeterminate form. So you would get the wrong answer if you applied L'Hopital's rule here. Don't do L'Hopital's rule in this situation right here. This is an easy limit to compute. We get 0 over 1, which equals 0. No L'Hopital's rule. Okay, so for our next example, let's look at this one. Limit as x goes to infinity. Square root of 3x cubed plus 2 divided by square root of 4x cubed plus x plus 1. Now, if you compute individually the limit as x goes to infinity of the numerator, you'll get infinity, denominator, you get infinity. So this is indeterminate of type infinity over infinity, which means that L'Hopital's rule applies. But just because L'Hopital's rule applies doesn't mean that you have to use it, right? There may be a better way to do it. And so here's what I want you to think about. When you compute a derivative, in many cases, the corresponding function gets less complicated, right? Derivatives often simplify things, right? When you take a derivative of a polynomial function, the degree goes down. So over in this example, when we took the derivative, x goes to 1. Things get less complicated. In that example where we had natural log of x over x, right? Natural log is kind of a complicated function. When we took a derivative, all right, we got a 1 over x. Things get less complicated in many cases when you take a derivative. But when your function, like these ones here, involves square roots, things actually get uglier, right? Derivatives of square roots usually get more complicated. So just because L'Hopital's rule applies doesn't mean you have to. There sometimes is a better way to do it. When I see square roots, I'm going to, in my head, I'm thinking, probably don't want to use L'Hopital's rule. So in this case, instead, what I want to do is just rewrite this as a single square root, 3x cubed plus 2 divided by 4x cubed plus x plus 1. And since square root is a continuous function, I can compute the limit of the inside and then take the square root of the result. And so what we get is the square root of 3/4, right, which would come out to be root 3 over 2. So just because you have an indeterminate form doesn't mean that you absolutely have to use L'Hopital's rule, right? In some cases, it's better to avoid L'Hopital's rule. Okay, so that was the first of our 2 indeterminate forms, and there's more. So the next one we want to talk about, all right, so the indeterminate form zero times infinity. And so how this goes, if limit as x approaches a of f of x equals 0, and limit as x approaches a of g of x equals plus or minus infinity, then limit as x approaches a of f of x times g of x, so now we're looking at this product right here, this is indeterminate of type 0 times infinity. So 0 times any other number, 0 times a number, of course, is equal to 0, but 0 times infinity does not necessarily equal 0, right? What it means is that further analysis is required. Now, here's how you handle this. So in this case, what we have is limit as x goes to infinity, x goes, approaches a, of f of x times g of x is equal to limit as x approaches a of f of x divided by 1 over g of x. Now, this will then be equal to, let's see, so now f of x is approaching 0. G of x is approaching infinity, which means that 1 over g of x is approaching 0. So by rewriting this as a fraction in this form, and all I'm doing is dividing by the reciprocal, right? So arithmetic, easy arithmetic would take us from one spot to the other. By dividing by the reciprocal of g of x, we arrive at an indeterminate form. And I could also do it the other way. I could write this as limit as x approaches a of, I don't want to write that. Okay, yeah, just do g of x divided by 1 over f of x. In this case, then, g of x is approaching plus or minus infinity. If f of x is approaching 0, then this fraction right here is approaching infinity, and so we get the indeterminate form infinity over infinity. So either one of these cases now is a situation where we can apply L'Hopital's rule. So now, apply L'Hopital's rule. So the point here if you have an indeterminate form of type 0 times infinity, you can't apply L'Hopital's rule right off the bat. What you need to do is rewrite the expression either in this form or this form, just divide by the reciprocal of one of the two functions, then you're in position to apply L'Hopital's rule. So let's look at a couple of examples. So first example, let's look at limit as x approaches infinity of x times tangent 1 over x. So let's see, as x approaches infinity, x is approaching infinity. 1 over x is approaching 0, so this tangent of 1 over x is approaching 0. So this is an infinity times 0. And so what I'm going to do, I don't apply L'Hopital's rule right away. I need to divide by the reciprocal of one of the two pieces. So what we have here, so this is a 0 times infinity. Well, let's get it in the right order. It's really infinity times 0. I divided by the reciprocal of x. Now what we have is indeterminate form 0 over 0, which means I can now apply L'Hopital's rule. And we get limit as x goes to infinity. Negative 1 over x squared secant squared 1 over x divided by negative 1 over x squared. I just took the derivative of the top. There it is, the derivative of the bottom. And now when we simplify it, this is the limit as x goes to infinity. The negative 1 over x squareds cancel. And what we have is secant squared 1 over x. As x goes to infinity, the inside is approaching 0. Secant squared of 0 is equal to 1. So what we just showed is that this limit right here is equal to 1. Next example, limit as x approaches 0 from the positive side, x squared times natural log of x. So as x approaches 0, x squared is approaching 0. As x approaches 0, remember from the positive side, natural log of x has a vertical asymptote, so it's approaching minus infinity. So this is a 0 times infinity. So now I wanted to divide by the reciprocal of one of those two functions. So I'm going to write this as natural log of x in the top and 1 over x squared in the denominator. And that will then give us an indeterminate form of infinity over infinity, which means that I can now apply L'Hopital's rule. So I'm going to take the derivative of the top and the bottom individually. The derivative in the top is a 1 over x. The derivative in the bottom, so this is x to the minus 2, which means that we'll get a minus 2x to the minus 3. And then let's clean things up a little bit. So this is equal to the limit as x approaches 0 from the positive side. So let's see, this will be a negative x squared over 2, right? And that's equal to 0, right? So this limit is equal to 0. So our next indeterminate form that we're going to look at, this one's maybe the hardest to deal with in the sense that there's no one way to approach it. So far we've seen if you get 0 over 0 or infinity over infinity, you can use L'Hopital's rule. If you get 0 times infinity, divide by the reciprocal of one of the two pieces. The next one we have, the indeterminate form infinity minus infinity. So let me just give an example. So there's no cut and dry way to do this. So let's just look at this first example here. Limit as x goes to infinity of square root of x squared plus x minus x. So as x goes to infinity, this piece is approaching infinity, this piece is approaching infinity, so we get infinity minus infinity. Infinity minus infinity is not necessarily equal to 0, right? It requires more analysis. It's an indeterminate form. Now, in this case, the trick for computing this limit, you got to kind of think back to Calc 1, and one of the ways that you can handle this is to multiply by the conjugate. So we're doing an algebra trick here. And multiply by the conjugate of this numerator in the top and the bottom. And now when we simplify, let's see what happens. This will give us an x squared plus x minus x. All right? Oh, no. It'll give it an x squared plus x minus x squared, so it leaves us with an x in the numerator. In the denominator, then we have x squared plus x plus x. So why did this trick help us? Well, it got rid of all possible occurrences of infinity minus infinity, and now what we have is the numerator is approaching infinity, the denominator is also approaching infinity, so we have an infinity over infinity. Which means that we could apply L'Hopital's rule, although if you remember our recognition last time is that when you multiply, or when you apply L'Hopital's rule to square roots, it can make things more complicated. So instead, what I'd like to do is remember another trick from Calc 1. This is kind of like a polynomial over polynomial. And the trick for dealing with that is to multiply by 1 over x raised to the highest power in the denominator. And in this case, the highest power in the denominator, I got an x squared under a square root. I got an x over here. The highest power is 1. And so when we multiply this out, what we get is limit as x approaches infinity of 1 divided by square root of 1 plus 1 over x plus 1. I'm just distributing, so if you multiply the 1 over x times the numerator, you get a 1. Multiply 1 over x through times the denominator, do a little bit of arithmetic, and here's what you get. As x approaches infinity, that little piece right there is approaching 0, and so in the end, what we get is 1/2. So that was sort of not expected, but it turns out the limit's equal to 1/2. So dealing with infinity minus infinity, here's a couple of things that can work. Conjugate. So if you see square roots, complicated square root expressions, this trick right here from algebra can help you. Second, getting a common denominator. So I think in some of your homework problems, just by getting a common denominator, that'll clear things up. It'll get rid of any instance of infinity minus infinity. Okay, so here's the last of our indeterminate forms. Indeterminate forms. So now there's 3 of them that are all lumped together here. 1 to the infinity, 0 to the 0, and infinity to the 0. These 3 right here are all handled the same way. And so I just want to jump in with an example. So I want to do limit as x goes to infinity of 1 plus 1 over x raised to the x. So as x approaches infinity, the inside is approaching 1. That exponent is approaching infinity, so this is indeterminate of type 1 to infinity. One of the very common mistakes that occurs in this class, and these are going to show up again in Math 143, is for people to think, oh, 1 raised to any power is equal to 1, so the answer is 1. False. This inside is not equal to 1. It's approaching 1, but it's never equal to 1. So what we have is some function not equal to 1, raised, it's approaching 1, but it's not equal to 1, raised to something approaching infinity. This is not equal to 1. So please remember this. This is an indeterminate form of type 1 to the infinity. And we deal with all of these indeterminate forms the same way. What I'm going to do is I'm going to let y equal the expression 1 plus 1 over x raised to the x. And now, think back to what we've been talking about when we were learning about logs. Log functions are designed to deal with exponentials. They help us handle exponents that are causing trouble. So what I'm going to do next is I'm going to compute, or I'm going to take the natural log of both sides. So we get natural log of y equals natural log of 1 plus 1 over x raised to the x. And then we have a rule of logs that says that this is equal to x natural log of 1 plus 1 over x. And so now what I'm going to do, instead of computing the limit of y, I'm going to compute the limit of natural log of y. So I'm going to compute the limit of this piece right here. So the limit, as x goes to infinity, of x times natural log 1 plus 1 over x. Well, let's see. X is approaching infinity. The inside of the parentheses is approaching 1. Natural log of 1 is 0. And so this is, I can't say equals, but this is infinity times 0. We just learned a few minutes ago how to handle that. I'm not going to apply L'Hopital's rule yet. What I want to do is divide by the reciprocal of one of these pieces, and I'm going to put the 1 over x in the denominator like that. Now, I have the indeterminate form 0 over 0. I can apply L'Hopital's rule. And I really want to emphasize, we learned a bunch of indeterminate forms. Only 2 of them are where we can apply L'Hopital's rule. 0 over 0 and infinity over infinity. All the others have to be manipulated first before you can apply L'Hopital's rule. And that's kind of the point, right? We're trying to get things in position, manipulate them so that we can actually use L'Hopital's rule. And now I can. I've got a 0 over 0. And so when I take the derivative of the top, let's see, I'm going to get a negative 1 over x squared divided by 1 plus 1 over x. And then in the denominator, I get a negative 1 over x squared. And I forgot to write my limit here. This is limit as x goes to infinity. Let me straighten things out here. Like that. Let's simplify things a little bit. So this is equal to limit as x goes to infinity. Now the negative 1 over x squared is going to cancel and leave us with a 1 over 1 plus 1 over x. As x goes to infinity, that little piece right there is approaching 0, and so we get a limit of 1. Now, the answer to our original problem is not equal to 1. What we just did is we showed that the natural log of y is approaching 1. So let's say that. So natural log of y is approaching 1. But we wanted to know the limit of y. We want to know what y is approaching. How do we undo the fact that we did a natural log? We exponentiate. So that tells us that y is approaching e to the 1. Exponentiate both sides of this to figure it out. And so what we just showed, and this was unexpected, limit as x goes to infinity of 1 plus 1 over x raised to the x is equal to e. That's kind of a famous fact. This is going to show up in this class, but also more importantly in Math 143. Right? This limit and limits very similar to this are things that you'll need to be able to compute. So let's do one more example. So let's do limit as x approaches 0 from the positive side of sine of x raised to the x. This is indeterminate of type 0 to the 0, and so what I want to do, I'm going to let y equal, you always do this for those 3 indeterminate forms, let y equal the expression. Take the natural log of both sides. Simplify using rules of logs. And so now we're looking at x times natural log of sine of x. So I'm going to compute the limit as x approaches 0 from the positive side, x natural log sine x. X is approaching 0. Sine x is approaching 0, which means that natural log of sine x is approaching minus infinity. So this is indeterminate of type 0 times infinity. So we then divide by the reciprocal, as we learned. So that'll be a natural log sine x divided by 1 over x. This is indeterminate of type infinity over infinity. Now I can apply L'Hopital's rule. So I get limit as x goes to 0. The derivative in the top is going to be a cosine of x over sine x divided by negative 1 over x squared. And let me clean things up a little bit here. So this is equal to limit as x goes to 0 from the positive side. So cosine over sine, that's a cotangent. Which, when I clean things up, or when I simplify, this is going to become a negative x squared over tangent. A cotangent in the numerator is the same as a tangent in the denominator. So if I flip and multiply, I'm left with this. All right, what is this? Well, this is a 0 over 0, right? As x approaches 0, both the top and the bottom are approaching 0. So we have an indeterminate form. That means that we can apply L'Hopital's rule again. So this is limit as x goes to 0 from the positive side, negative 2x divided by secant squared x. Okay, so let me put a little LH there. I applied L'Hopital's rule. And I should point out, right, every time you get an indeterminate form, you can apply L'Hopital's rule. Sometimes when you take the derivative of the top and the bottom, right, you get another indeterminate form, which means you can apply L'Hopital's rule multiple times. But in this case now, so let's see, as x approaches 0, the numerator is approaching 0, the denominator is approaching 1, so we get 0 over 1, which is 0. So what did we show? We showed that this limit right here is approaching 0. To undo that process to get the actual answer, exponentiate. So we would say so limit as x approaches 0 of sine x raised to the x is equal to not 0, but e to the 0, which is equal to 1. All right, so that's it for indeterminate forms and for limits. This material will show up obviously in this class in future sections. Also, it's extremely important for you to be able to use L'Hopital's rule and these various manipulations so that you can apply L'Hopital's rule when you're learning about series, infinite series, when you take Math 143, right? So this is not something that you can just forget after this class, right? This will show up again later on. Okay, see you next time.